And exponential functions have an exponent in them, meaning that it's not going to be linear. It's not a linear relationship. If you get a line, a linear graph, you're in trouble. Okay? So, exponential functions. An exponential function, by definition, is a function. And what was function a fancy word for? Equation. Y equals something. An exponential function is a function, which is a fancy word for equation, where the independent variable the x value the number of days. We can't manipulate time, right? The number of people. And the independent variable is an exponent. What do you think happens when you use exponents? Not what do you think. What do you know happens when you use exponents? Like, what happens to a number? What if I have the number 5 and I give it an exponent of 3? What happens to it? Dean? Yeah, it multiplies by itself. So 5 times 5 times 5 is 125. So we went from the number 5 to 125. What happened? Got bigger. And did it get a lot bigger? Yeah, exponents get big fast. 5 to the first power is 5. 5 to the second power is 25. 5 to the third power is 125. I mean, it gets big fast. You don't want to have to do, without a calculator, 5 to the 10th power. It's too big. It's only 10 things, but it's too big. So these problems are going to get big, and they're going to get big quickly. So here's an example. Remember, f of x is function notation. I could rewrite this as y equals, correct? Are those both interchangeable? Yeah, this is function notation. This is y equals notation. Like, this is our graphing notation. But they're both the same thing. And if I had this equation, that's an exponential function. Because there's a variable that's an exponent, by definition.
Would it still be an exponential function if the x was the base, not the power?
So Zach's asking, what if it was written, don't write this down because it's incorrect. If it was like this, no, we want our x, our variable, to be the exponent. I mean, it's still a function. It's a different type of function, but it's not an exponential function. An exponential function has to have the variable, our x value, as the exponent. So it's a good question. And this is a real function. This is a real equation that's used in life. This equation represents the number of insects in a population after X days. I don't remember the exact insect, but let's pretend it's fruit flies. Fruit flies spawn really quickly. So if you were doing in science class an experiment, fruit flies are used quite a bit. If you were experimenting with fruit flies, can you tell me what would be the population after 5 days? So I'm going to substitute. They tell me 5 days. That's my independent variable. Because in 5 days, what's going to change? The number of fruit flies. The number of fruit flies, or whatever this is, depends on how many days. So f of x equals 2 times 3 to the 5th. You could do this mentally, or what could you use to help you? A calculator. Three to the 5th. 3 times 3 is 9. 9 times 9, 84 times 3 is 81. 243?
Yeah.
And 2 times 243 is, double it, 486. In 5 days. On the first day, you had how many insects? Can you figure that out? First day, day number 1, how many insects did you have? 6. 3 to the first power is 3. Times 2 is 6. On day 1, you had 6 bugs. On day 5, you had 486. Did that get big? Did it get big fast? Yes. Exponential functions get big fast. So could you, if you were given a function, could you use it? Like if you're given an equation, could you substitute values in to solve? Yeah. I see something that I should have probably changed. Nobody caught it though. Why am I whiting out the x? Because I should put the number 5 in it, because that's the number I'm substituting. The function of 5 in this equation is 486. You want that? Is that what you're asking for? Does this 5 right here impact anything? Do I do any math with it? No. It's just telling me that's the number that I substituted. Okay, so the second type of problem you're going to have is you're going to be given a relation, which is a group of ordered pairs. You're given a relation, you're given a set of ordered pairs. And I'm going to ask you, all right, smarty pants, is this an exponential function? And you're going to be like, I don't know. How do you tell if a relation, if you're given ordered pairs, how do you know if it's an exponential function? I mean, you could graph it, but you're not given a graph, so that kind of seems lame. So to figure it out, we put it in a table. Just because sometimes vertical is easier to read than horizontal. Some of you can do it without putting it in a vertical table, the more you practice. So my first ordered pair is -1, 1.5. My next ordered pair is 0, 3. My next ordered pair is 1, 6. And my next ordered pair is 2, 12. And if you remember back to linear functions, hopefully, fingers crossed, you think back to linear functions, we had to find the change in y over the change in x. Right? We had to find the slope, basically. And we're going to kind of do that this time, but it's a little bit different. If I look at my change in x from -1 to 0, what happens? It increases +1. From 0 to 1, what happens? +1. From 1 to 2, what happens? This is what we want to have happen. We want this to be constant. Or if it's not constant, we want it to be proportional. If it increased by 1, it increased by 1, and then it doubled, it increased by 2, we'd want this over here to be the same, and then doubled. Right? It needs to be proportional. We learned that in pre-algebra. But here's the change. For exponential, for linear functions, I'd look and I'd say, okay, 3 plus what is 6? And 6 plus what is 12, right? I'd want to add the same time. Exponential functions, we multiply or divide the y differences. Does that make sense? Our change in y value needs to be a multiply or a divide in order for it to be exponential. If it's an add or subtract, it's linear. But if it's multiply or divide, it's exponential. If it's neither, there is no pattern. It's not a function yet. So let's look. 1.5 to get to 3. What can you do to 1.5 to make 3? Dean? Times 2? From 3 to 6, what do you do? Times 2. And from 6 to 12? Times 2. So is this relation exponential? Yes. And why is it exponential? It is exponential because why? Okay, it has a pattern. What's the pattern, Raina? The y value is always multiplied by 2. Or, what Julie said, has a multiplication pattern. Or it could have a divide pattern. We're going to make a graph. Do you guys want one? That's true. All right, so to graph. let's graph this relation just because it's small and easy to do. Let's graph this relation on this graph so that we can see what a picture looks like, and then we'll talk a little bit about the act of graphing. So my first ordered pair is -1, 1.5, and I get it, like decimals are hard. Move on, get over it. So -1 up 1.5. Then I have 0, 3. Then I have 1, 6. And you're going to have to use your imagination. 2, 12. And if I wanted to put one more dot on my graph, let's go backwards one. So instead of going down, we're multiplying by 2. If I want to go backwards, what's the opposite? Divide by 2. So what's $1.50 divided by 2? 0.75, right? 75 cents. So, and then go backwards. Here I'm adding 1, so going backwards I'm going to subtract 1, so it's -2. So if I look, -2 and 75 hundredths is about right there. I mean, again, you're estimating. So, exponential functions curve. Right? And, you know, I can... And if you look at that graph, see, your dots start out really close together. And then they get further and further and further apart because those numbers get big fast. So what you need to be aware of when you're graphing, like, you know, pitfalls, things to watch out for. It needs to curve. If it doesn't curve, you've got a couple options. Either you're graphing wrong, right? Your math is wrong. You're substituting and you're not doing the exponent right. Or, I mean, there's something wrong there. So double check your math if it doesn't curve. Also, if it doesn't curve, your numbers just may be like so big, so gigantic that it's not going to curve. The curve is really seen when your numbers are close together, when you have 0, 1, and 2. So that being said, if you're given the option of, hey, here's an equation, you should graph it, and you have to pick what numbers to substitute, you should pick 0, 1, and 2 to substitute. Here are the reasons why you should pick 0, 1, and 2 to substitute. It's easy to substitute, to use an exponent of 1. Does an exponent of 1 do anything? No. It's easy to use an exponent of 2, squaring something. You're pretty good at multiplying a number by itself. Anybody remember the rule? An exponent of 0? It's always 1. 10 to the 0 power is 1. 42 to the 0 power is 1. So these are easy numbers to substitute. Also, when you square something, I mean, yeah, it could be big. But if you cube something, is it most likely going to be off your graph? I mean, you think about it. 2 cubed, 2 times 2 times 2 is 8. You could still graph that. But 3 times 3 times 3 is 27. That's well off our graph. Am I saying never pick anything else? No. But I'm saying maybe throw in, if you have to have a negative, it's always good to have a negative, throw in a -1.